All right, so we're looking at chapter 4 of the BVH series, and we're talking about animation. So, exploring the wonderful world of bounding volume hierarchies, mysterious data structures that enable real-time ray tracing on recent GPUs in complex animated scenes. Despite the broad adoption of many of ray tracing in games, uh, in-depth understanding of the underlying technology seems to be reserved for a select few. In this article, we show how a proper BVH is implemented without support for DXR, RTX, optics, or Vulkan in easy to read, sane C++. Whether this is actually useful for you or just interesting as background information depends on your needs, obviously. The series consists of 10 articles, and for the full source code is available on GitHub. So the fourth article, we're going to start looking at rendering animated scenes. So let's start with some modifications to facilitate the introduction of some new concepts. We'll need a new model. So we've got one of the Westminster clock tower. Just the tower, without textures, in grayscale. Sorry. 3D rendition. This guy's actually pretty funny. I met him at HPG. He's an interesting guy. The rendition of the tower has 20,944 triangles, which will tax the BVH builder a bit more than the Unity vehicle in the last chapter. Rendering the slender objects, on the other hand, is faster as it occupies less pixels. So we have fewer arrays are going to hit it. Let's focus on BVH maintenance for this article without worrying too much about rendering performance. Speaking of rendering performance, here's a new tick function with an adjusted camera and a somewhat fine-tuned open multi-processing, OpenMP multi-threading. So we have the Pragma OMP parallel, blah blah blah. That is to parallelize the for loop. And so we are looking at doing it in tiles. We have looks like define array origin, then kind of a U and a V, doing like a something to index inside of the tiles, then intersect the BVH, and then plotting C is the ray.t is less than the max distance constant that he sets. It's basically a remapping of the distance to the intersection. So looking at a grayscale clock tower that renders in 4 milliseconds. Rendering the BVH using this 8-plane binned builder takes about 30 milliseconds. Building the BVH, sorry. Not as shiny as the original photo, but it will have to do. So, being flexible. So we have an animate function that's going to iterate through the triangles and apply 2D rotation for each vertex, sine wave scaled by the Y position. Okay, stiff breeze is bothering the tower. So animation code requires a copy of the unmodified triangles. So we create room for 2 copies of the triangle set. Array try contains the input for the BVH builder. Array original stores the unmodified data. The init function now thus reads to the original array. Okay, and since we're now changing the mesh each frame, we should build a BVH each frame as well. This requires a few small changes to the build BVH function. First of all, it should not allocate the BVH node array each time we build the BVH, so this needs to be allocated elsewhere. Second, we need to reset the pointer to the next free node in the BVH node array by setting nodes used to 2. Recall that BVH node 0 is the BVH root node, and BVH node 1 is skipped to ensure that subsequent pairs of nodes reside in the same cache line. With these changes made, we can now call the new animate function and the updated build BVH function once per frame in the tick function to obtain the desired ray trace animated scene. Second. Okay. So let's see. Okay. If the animated flexible Big Ben is now, if it fits, if the animated flexible Big Ben is now being ray traced in real time, if your system's faster. On my machine, I get about 30 FPS, he says. For if the total frame time, about 30 milliseconds, spent on building the BVH and rendering is about 4 milliseconds. Seems like we may have a problem for more complex scenes or a mesh that covers more pixels. May have to come up with a smarter solution to stay real time under those circumstances. Let's take a look at a very simple animation, one in which the clock tower takes off for a trip to the moon, boldly going where no Big Ben has gone before. The 3 frames that have something in common, the BVH. For the construction of each of the 3 BVHs, exactly the same decisions are made. With the same number of nodes and the same number of triangles in each leaf node. The only difference is the bounds that we will store in every node. These will have a vertical offset. Obviously, there's a better and faster way to handle this type of animation. By moving the missile up, we can move the camera down to obtain the same result without ever rebuilding the BVH. But what if the animation is a little different? This time, moving the camera isn't going to work. We cannot, and we also cannot simply assume that the BVHs differ only in their bounds. They are going to be rather similar, though. What if we would, in fact, use the same tree with updated bounds only? It certainly would save a lot of time in construction work. The technique where we use the BVH for an animated mesh is called refitting, or where we reuse the BVH. The process starts at the leaf nodes, which now contain the now changed triangles with their new positions. Each leaf node gets an updated bounding box. The update may have consequences for the parent nodes of the leaf nodes, so we adjust their bounds as well by making them tightly fit over their child nodes. We proceed this way until we reach the root of the tree. It sounds like a recursive practice, but in practice, or recursive process, but in practice, a simpler approach can be used. When we created BVH, we always used node O for the root, or node 0. After that, each child node got allocated after its parent. We thus know that the the index of a child is always greater than the index of the parent. We exploit this by visiting all nodes starting at the end of the list, working our way back up to the first element. This reversed order guarantees that we never visit an interior node with outdated child nodes. Interesting. With this trick, the refit functionality becomes rather simple. Starting from the end of the list, going down to 0. If the node is a leaf, update the node bounds and continue. Otherwise, we're going to look at the 2 children, which will have already been populated because they're, yeah, okay, that's pretty cool. In words, we visit all the allocated nodes starting at the last and skipping node 1. If the node is the leaf, we recalculate its bounds using the triangle it contains.
Recording in
There's echo coming from someone's mic.
Was it anyway, yeah. For interior nodes, we adjust the bounds so they enclose the 2 child nodes. The whole procedure is pretty simple. It completes in half a millisecond. This means that the flexible tower now gets updated and rendered in less than 5 milliseconds. We're actually ray tracing a dynamic scene at 200 FPS, unoptimized and all. So that's pretty interesting. So refitting with the same divisions made in the tree. It's just refitting the bounds and then the parent bounds for the updated primitives. It's interesting. Okay, interesting. Yeah. Okay. Based on the findings so far, I would assume that BVH refitting is a golden bullet to handle all animation. This is sadly not the case. For starters, refitting requires that the animation frames have the same number of triangles. Also requires that the structure of the animations frames is roughly equal. Consider the following situation. Here, the large triangle moved a bit, invalidating the right bounding box. Not a big deal. Refitting is quite effective here. Adjust the right box to tightly fit the new set of primitives. We adjust the root box. It becomes a bit smaller on the right side and the bottom. But now we have to consider a different situation. This time, one of the small objects from the top left node moved all the way to the bottom right of the scene. If we update the top left box to include the moved object, the resulting box will be massive. It will almost entirely overlap the right box. Quite obviously, the resulting tree is rather bad, because that node is going to span basically the entire range that's covered by the BVH. So yeah. Yeah, a much better choice would be to include the moved object in the right node, but that's not what refitting does. In general, refitting is applied when we have subtle animation. This is things like trees waving in the wind, objects changing position, perhaps in some cases a walking character. In those cases, we get a BVH update almost for free, often at the expense of some tree quality. In other cases, a rebuild would be a better option. We can also combine rebuilding and refitting. In that case, we refit some subsequent frames, and after a few refits, we rebuild to ensure that the BVH doesn't deteriorate too much. A well-designed ray tracing engine will strive to rebuild a few meshes per frame while refitting the others. So we're taking a look at a ray tracing, or from a racing game rather. How should we build the BVH for this animation? We have a few different situations. The track is large and static. We should build a high quality BVH one time for this. Race cars move but do not deform, so they should be refitted. Okay, that's it. Okay. Audience next to the track goes through a simple animation sequence. We could pre-calculate a small set of BVHs for this. Challenges, of course, is in the combination. And how to handle this is the topic of the next article. Okay, a little bit shorter one, I guess.